Hey guys, Marco. My name is Marco Elledge. Thanks for coming tonight. I'm one of the staff of KiwiSpace, along with Mark Mackay and Billy Cook here. First meetup of the series, hopefully. The series will be two or three more to come. Thank you to Sergei, Professor Sergei Gulyaev, from the Institute of Radio Astronomy and Space Research, giving our first talk for our first meetup. Okay, great.
Okay, thanks, Marco.
Any Q&A will be what you have to say, and
Thanks, Marco. Thanks, Mark, for inviting me, and thank you for coming to this little, I would say, informal meeting, just to have a chat about everything. So, you are people who are interested in space and everything connected with space flights and so on. I'm not that kind of person. I was educated as an astronomer, classical astronomer in Moscow State University, and we had, it was based in physics department, so we had to go through all, mathematical courses, very serious, and plus physics, including theoretical physics, like quantum physics, statistical physics, and so on. Plus, to this, many astronomical papers, starting from like spherical astronomy. Do you know what spherical astronomy is? Oh, it's about different types of time and different coordinates, celestial and coordinates here on Earth, and so on, and precession, nutation, aberration, all these kind of things. And papers in astrometry and stellar astronomy and astrophysics and gravimetry and celestial mechanics, beautiful names. I should say that I was lucky. I was born before the first space flight, before the 4th of October 1957, Sputnik. People sometimes pronounce it as Sputnik, but actually a Russian word is Sputnik, which means satellite, Sputnik. And then first man flight, and then the first woman in space, first space walk, and then first group of people in space, and then first flight to the moon, and so on and so on. And here we are now. Space flights are just something which is not very unusual. But at the period when I grew up and thought about where to go, who to be, I was actually heavily influenced by all these space things around, and science fiction, many things like Stanisław Lem and Fred Hoyle and whoever, Brother Strugatsky. Do you know Strugatsky? Yeah, that's fantastic. Oh, it's incredible. So and actually when I was like that, I was always walked and looked at the sky, keeping the hand of my father, and that was like that. Sky. And sometimes people ask me why New Zealand, and my answer is simple: because of the southern sky. It is not very well investigated, studied, not like the northern sky, northern hemisphere sky. So New Zealand is the ideal place for this. So back to education. In the year 3 of the university, we had to decide which specialization to take, and I took a specialization connected with astrophysics and radio astronomy, and then I did my master thesis in radio astronomy, and then PhD, and after many years it was called DSc, another one, Doctor of Science, and it was all in astrophysics and radio astronomy. The things that I was interested in was connected with the space plasma and areas of star formation. So again, no connection with space flights, but of course space flights happens around all the time, and we learned and learned about it. And probably Mark met many more astronauts in his life than me. The first astronaut I met was Buzz Aldrin. I met him here in New Zealand. We had a nice talk and great, great photos. And the second was Masha Irvin from NASA. Incredible woman. Her flights were connected, like she flight actively before the first catastrophe with the shuttle, and then there was gap, and then she started flying again, and then the second catastrophe. So just woman legend, incredible. And I found that we were born at the same year, so we had a very good talk. And I told her, look, I looked at all this space race from one side of the Iron Curtain. You looked from another side, and you know, it's very, very interesting. I told you that Moscow State University so means Russia, basically. And I was born in the Urals. You know, the Ural Mountains at the border between Europe and Asia. Yeah. And then when I did my master degree, I started actively working in radio astronomy, and it was Radio Astronomical Observatory, where I collaborated and worked with radio telescopes, but also because it was space plasma and stellar star formation and ionized hydrogen areas and formation of spectral lines. I also observed at that time, the biggest optical telescope. You will probably smile now. The biggest, what does it mean? At that time, it was 6-meter diameter. The mirror of optical telescope, 6-meter diameter, maybe from there to Maka or even more. Huge one and the telescope itself, optical telescope, with 4 elevators, 4 lifts, so you can go to on the 5th floor it was spectrometer, on the 4th floor it was polarimeter, and so on and so on. Very, very interesting and exciting. Okay, so when I came to New Zealand, actually I found that the closest radio telescopes are in Australia. And it's possible in modern days to observe in any radio telescope or optical telescope in the world. This is the concept of the free sky. Free? No, not free. Yeah, okay. When you can use any telescope or radio telescope. Users need to write a proposal, submit it, and if the committee peer review thinks that this is good enough, you will have observational time. And sometimes your observational time is like 40 minutes. Sometimes you need 40 hours. Sometimes you need 300 hours. Well, there are different tasks and problems. But no radio telescopes in New Zealand. And at that time, I already had a position in Auckland University of Technology. I was invited to be deputy director of Earth and Oceanic Research Center at that time, and then Earth and Oceanic Science Research Institute, EOS Institute. My colleagues and I started thinking about what can we do in terms of radio astronomy. We found, we were lucky to find a small amateur radio telescope, 6-meter radio telescope, and 6-meter diameter. And it's interesting, 6-meter optical telescope was the biggest in the world, but 6-meter radio telescope, it is tiny, it's small. What can you do? Collecting area for radio waves is very small. Sensitivity is very small. But in radio astronomy, we have this special technique which is called very long baseline interferometry, VLBI. you can use very big radio telescope, like 64-meter diameter radio telescope, which is in Parkes in Australia, and 6-meter. And these two telescopes will be equivalent to two telescopes with collecting area of square root of the product, 6 times 64. So altogether, it's like observing with 20-meter nice radio telescopes, which are big enough, good enough. And if you have several more radio telescopes, you can produce image of radio astronomical objects. And for image, it's very important to have very fine resolution on the sky. And in the VLBI technique, very long baseline interferometry, when you look at this object with the baseline, for example, between us and Parkes of 2,000 kilometers, it's equivalent of observation with a radio telescope with the dish of 2,000 kilometers diameter. So you have huge angular, very fine angular resolution. The size of the pixel is like as if you observe with a huge radio telescope. But of course, collecting area is small, so sensitivity would be not high enough. But there are very bright objects on the sky. So we started from 6-meter, and then pretty quickly AUT decided to invest in this area. First of all, probably it was connected with the fact that we started participation in the Square Kilometre Array project. And I was asked here several times today, are you going to mention about the Square Kilometre Array project? Yes, I'm going to mention, because actually my involvement started in 2004 when I met one very interesting guy from Australia in the conference in Tokyo, in Japan. It was the conference of International Astronomical Union, of which I'm a member, and he was the president of the International Astronomical Union, Australian, Ron Eckers. He was the director of CSIRO and all radio telescopes in Australia, and before that he was director of VLA, Very Large Array in United States, and a fantastic person. And I just complained, saying that, look, we don't have radio astronomy in New Zealand. But he said, well, but you have Ian Exford. At that time, I didn't know who Ian Exford was. It was actually a fantastic person, Sir Ian Exford, a New Zealand of a year, I don't remember which year. He made his career in United States, in Europe. In the United States, he was in professor of Columbia University. He started with Carl Sagan, that famous Center for Radio Physics and Space Research. And then he became director of Max Planck Institute for Astronomy, and they developed many space flight, modules at that time to investigate Jupiter and Saturn, and they flight on Voyager and Pioneer and other things. So I met with Ian Exford, and he was actually happy to support our idea of development of radio astronomy in New Zealand and our idea of collaboration with the Square Kilometre Array. So we flew to Australia, to CSIRO in Australia, to a meeting of Australian SKA Consortium Committee, and I gave a presentation and showed, actually, look, if SKA comes to Australia and supposed to occupy with thousands of telescopes the whole Australian continent, how about if we build part of it in New Zealand? The baseline will be, instead of 3,000 kilometers, will be almost 6,000 kilometers. So huge improvement in terms of resolution, image quality. Well, historically, and we started working jointly with Australia. They were very excited about this idea, and we started working together. And AUT, Auckland University of Technology, and New Zealand became involved in the Square Kilometre Array. We created SCAN's Square Kilometre Array New Zealand committee with Sergei Gulyaev as the chair of it. And AUT at that time invested in a bigger radio telescope, 12 meter in diameter. Altogether, it was like investment of order of $1 million. We had to find the place. We had to equip this place properly for the radio telescope, and then we had to make it working. Because radio telescope, it's not like buying a car. You buy a car, you put your key, start, and you go. No, with radio telescope, it's not like that. You need so many other things to make it work. And one of the most expensive things is the maser clock, hydrogen maser clock. That's the standard of atomic clock, standard of frequency and time. And it costs like 200 to 150,000 New Zealand dollars at least. And we bought it. So, and then we faced the situation that almost every day we had some problem with horizontal motion, problem with vertical motion, problem with receiver, problem with connectivity that we had, and so on. So a radio telescope, it's a lot of work and effort. The Square Kilometre Array is going to consist of many radio telescopes like our 12-meter radio telescope. Well, actually, they will probably be 15-meter diameter radio telescopes. And in South Africa, there will be an array of 3,000 radio telescopes, 15-meter diameter. And they will be distributed in 7 countries of Africa, with the core in South Africa, in Kuru Desert. But it will be just one part of the Square Kilometre Array. Other 2 parts will be built in Australia. One will be low frequency array for special objects and investigation of sky in low frequencies, and for problems like epoch of reionization. That's a very special period in the history of evolving universe. Now we know what's happening today. We know what's happening, a few billion years ago, because telescope and radio telescope, it's like time machine. If the object is like 4 billion light years away, when you receive these photons here today, they are 4 billion years old, and they bring you information about this object as it was 4 billion years ago. But the age of the universe is 13.8 billion years. And we know about first few thousand years of the universe, and then huge gap from 13.8 billion years ago to like 5-6 billion years. And in between this period, there was an event called epoch of reionization, when first stars and galaxies started forming. And if we manage to find the signature of this epoch of reionization with the help of low-frequency radio telescope array, only SKA will be capable of doing it because of sensitivity. We will have another very strong confirmation of the Big Bang theory. Probably we don't need more, but it's possible to find another just final nail, in our understanding of the evolution of the universe. And also we will learn when star formation, galaxy formation started in our unique universe. So, and the third instrument that will be built part of SK in Australia is called the Survey Telescope. It will be another revolutionary type of radio astronomy. It's well, probably I shouldn't go in details, but if you ask me in the question and answers period, I am happy to tell more about it. So due to our involvement in the Square Kilometre Array, it was decided that it is a strategically important area in for New Zealand because radio astronomy unites astronomy, computer science, everything about computer science, like hardware, middleware, software, engineering, mechanical, electrical, electronics, connectivity, all this networking, every area. So it may be important for New Zealand, and the government decided to give us just initial $1 million to participate in the design phase of International SK. And this is what we do, and we have New Zealand SK Alliance, and my colleague from School of Computing and Mathematical Sciences in AUT, Andrew Enser, is the leader of this and project manager at the moment. So the next step was the fact that 12-meter telescope is not big enough to solve important problems of radio astronomy. And before SK will be ready in 2025, maybe 2024, we want to do some important research in this area of radio astronomy and astrophysics. And we talked to Telecom New Zealand, who had 2 telecommunication antennas, 30-meter antennas, and about maybe acquiring one of them. And they gave us one of 30-meter antennas. The second one was demolished, but the newest one, the biggest one, was given to us. And we were lucky that our 12-meter telescope was built near this telecom station with 30-meter, and now we use 2 radio telescopes. We just started using 30-meter telescope. This is between us because the formal first flight of the 30-meter radio telescope will happen on the 4th of July. That's when we will have government people. They talk about prime minister, I'm not sure, but hopefully 1 or 2 ministers and so on, and they will push the button. And telescope will start moving, and we will see on the screen some spectral lines of methanol molecule from star formation area will start oozing from noise. So you will have huge noise, and then noise getting smaller, 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 and then you see this beautiful spectral line of methanol maser that tells us about some stages of star formation. So this is what will happen on the 4th of July. But of course, between us, we internally already saw it, and we know that it's all working. Now we're just thinking of where to take a big button so 2 ministers and prime minister could put their 3 hands on this. Now, right. What else do we do? Apart from my favorite and old area of astrophysics and star formation, we use our 12-meter radio telescope. I'm not talking about 30-meter yet. 12-meter radio telescope for geodetic research. In fact, radio astronomy gives very important information for study of our planet Earth. Its rotation, its irregularities of its rotation. The radio the Earth the polar axis motion of the Earth, the tectonic plate movement. Why? Because we are very lucky that we, radio astronomers, can see the most remote objects in the universe, and they are quasars. We know several thousand of quasars, and at least 1,000 of them form the fundamental reference frame, which we call the radio astronomical geodetic reference frame, or celestial reference frame. And we observe these quasars with the network of radio telescopes around the Earth. Several dozens of radio telescopes are involved. This is called the International VLBI Service for Astronomy and Geodesy, Astrometry and Geodesy, sorry. And we just monitor the position of these quasars, and looking back to our Earth, we can tell about its motion, rotations, vibrations, and tectonic plate motion. So we just preparing a publication about first results of 3-year observations with our Warkworth radio telescope, 12-meter radio telescope, and several Australian telescopes which are designed for the same purpose. And we see, yes, when we look at, for example, the baseline, Warkworth and Hobart, they have in Tasmania similar 12-meter radio telescope. The baseline is huge. It's almost 2,500 kilometers. I don't remember exactly. We look at residuals. We look at what happens with this 2,000-3,000 kilometers baseline, and we see variations, seasonal variations, annual, semi-annual variations on the level of a few millimeters, amplitude of 5 millimeters only. And also we see that there is some interesting trend on increase of this baseline. The baseline getting larger with the rate of some 4 or 5 millimeters per year. What does it mean? We don't know yet. Maybe New Zealand keeps going away from Australia. So we need to study this. But people who are involved in geoscience here in New Zealand and in Australia are very interested in this development and this observation. So not only astrophysics, but also earth science. And in New Zealand, which is sitting on the border between two tectonic plates, North Island is mainly on Australian tectonic plate, and South Island mainly on Pacific tectonic plate. And all these earthquakes and volcanic activities because of the... Oh, only, okay. Okay, is because of this tectonic plate motion. For New Zealand, it's very important. Another area of our involvement is involvement in space research connected with space agencies, different space agencies. Actually, when we talk about space, and here I'm in the meeting of KiwiSpace people, what do we mean by space? Like International Space Station, right? Of course, it's in space, yes. But if you imagine, for example, the Earth with a radius of 1 meter, so diameter would be 2 meters, like this, right? 2 meters. Where is the International Space Station? About 300 kilometers. 300 kilometers is 1/20th of the radius of the Earth. 1/20th of 1 meter would be 5 centimeters. So, okay, the Earth, and here's the International Space Station. Space, right? Yeah, but what we know, of course, it is above the atmosphere, and the thickness of the atmosphere is approximately 100 kilometers, and even it's above the ionosphere. So yeah, it's definitely space. So we were approached by several space agencies, and I think it started first from JAXA when they approached us and said, "Hey guys, you're in very good geographic location to observe 2 of our satellites, not satellites, 2 of our missions that we are going to launch." And these 2 missions were Icarus, that's a different abbreviation from the name of this ancient hero, Icarus, and Akatsuki. And they were sent to Venus. And actually, Icarus was the first ever solar wind sail. So it's supposed to, at a certain stage, when it is, start moving towards Venus, it's supposed to open its sail, and we had to observe whether it really has acceleration that is made by the solar wind. It was very easy to do. We knew where it should be on the sky, and it radiated a tone at certain frequency. So we observed position of this tone in the frequency scale. And we saw that if you have a constant velocity, you deal with the Doppler shift. So your signal will be just shifted to a constant value from its laboratory frequency. But if it has acceleration, then you will have a drift. And we found that yes, it has a drift, and not only acceleration, but the next derivative. So it was pretty successful, and showed that acceleration is provided by the solar wind indeed. And then people from ESA and people who work in Europe with ESA, radio astronomers, approached us and said, "Hey, you have a beautiful geographic location, unique in the world. Can you help us with observation of Mars Express and Venus Express?" And actually, if you remember, this Mars Express was launched, reached Mars about 10 years ago, and it is there for orbiting Mars for 10 years already. And sometimes when it goes around Mars, it meets, has flyby near Martian satellites, moons, Phobos and Deimos. One of them, Deimos, is a piece of rock of like 10 kilometers in diameter. Another is about the same size, 10 to 15 probably kilometers diameter, Phobos, but it's pretty mysterious. If you look at the pictures of Phobos, it looks like, like a cigar with some interesting lines across it, and with a big hole inside. Well, very strange object. And people started studying Phobos for long ago, and looking at optical observations from Earth, decided that something's wrong about it. It looks like it has very small density, small mass for certain volume, density. And there was even hypothesis that maybe Phobos is hollow inside, and sort of artificial, maybe Martians use it as International Space Station of their Mars, of huge size, like 12 kilometers. Nice International Space Station.
Have they done any more discoveries in, as far as Mars is concerned on the light planet form?
Not yet, as well as I know. But in terms of Phobos, it was decided that when we have this flybys of Mars Express near Phobos, we can look at gravitational acceleration, gravitational force that Phobos produces when Mars Express comes nearby. So again, the same game of acceleration, and we can determine exactly what happens, and then celestial mechanics can compute all this and come with the mass of Phobos. We know the size, we have photos, but what is the mass? And the mass was determined, and it proved to be indeed very low. So it is the density, if it is made of some kind of rock. No, you can't imagine a rock with density of water, right? So if it is made of rock, it means that it has huge sparsity. You know, it has huge holes. These rocks are not well sitting close together, but at the same time, size is big enough during the long period it would come to one object. So still people think maybe it is made of some kind of steel and hollow inside. So there was a Russian mission, unfortunately not successful. Phobos grunt, Phobos soil. Grunt is a German word and Russian also for soil. And it's supposed to anchor Phobos and drill inside. But something happened on the orbit of the Earth and was lost, and unfortunately we still don't know what Phobos is. And one day I had a call, and the guy said, "Oh, we're calling from a company called SpaceX. You have a beautiful geographic location. Would you like to consider maybe helping us, because we're doing these launches, and we are the first commercial company which is developing the substitute for space shuttle." And we said fine. We always say fine, why not? And we started participating in SpaceX from point of view just tracking. So when they have launch, after for a few orbits, they need telemetry information, and they have several tracking stations around the Earth, and ours is one of them. And when it flies over New Zealand, we know where it will appear above the sky, above the horizon. We catch it with our telescope and we follow until it goes below the horizon. And during this period, which lasts normally some 5-10 minutes, quite a lot of information can be transmitted from SpaceX capsule to us. And it goes, of course, to this ballistics and celestial mechanics, and they check the orbit, update the orbit. They get some other information. For example, it's video information also. I remember one day we were doing this things after it docked the International Space Station, and we just listened them talking to the International Space Station people, and they said, "Okay, so we are ready to open the hatch and start taking the goods and all this stuff." Said, "Oh, wait, in 10 minutes you will be over New Zealand, and then we will have video and we will transmit it everywhere. And we also have live, broadcast from SpaceX on the computer, and in 10 minutes our telescope grabbed it and started going, and it was quite a pretty high elevation, so it lasted more than 10 minutes, maybe some uh, 12 minutes or so, and we saw them standing near the hatch. Said, "Okay, you can start." And they opened it, and they flew inside and started doing some funny things. And then the camera inside of the Dragon capsule, that SpaceX capsule, started working, showing them entering, and it all went through us, our 12-meter telescope. Cool. Yeah. By the way, now it is attached to International Space Station. That's flight number 3. Before that, there were a few test flights, but this is not considered as test flight, just another 3rd flight. And on Sunday, tomorrow, 13 hours Greenwich Mean Time, it will have to undock the International Space Station and start some its own orbits and then prepare for landing. 13 hours Greenwich Mean Time means about 1 a.m. on Monday. Not very good time, but we're astronomers, and that's all right. So, yeah, very interesting. Another collaboration that unfortunately didn't quite happen was with Russian Space Agency. They supposed to launch the Space Radio Telescope. The Space Radio Telescope of quite significant diameter of 11-meter diameter. So they launch it, and then it opens like umbrella and starts working as a radio telescope. There were space radio telescopes before, well, actually one. It was Japanese space radio telescope. It was orbiting Earth, a little bit higher than International Space Station, and we had very interesting data and some discoveries, astronomical discoveries, but still it was orbiting Earth on almost circular orbit. But this Russian project supposed to go from the Earth to the Moon and then back to the Earth, and then so orbit was very elongated ellipse. And for us, for radio astronomers, astrophysicists, the greater the baseline, the smaller objects we can see. It's like taking better and better microscope and looking at your little things in biology or whatever. So, and they launched it, and they needed tracking stations, and we talked about it because that was very interesting to work with Space Radio Telescope. But unfortunately, they preferred to deal with South Africa, and they have tracking stations there. But as they fly, sometimes we and Australian colleagues work as radio telescopes to create images, not just to track, but work jointly when they observe some celestial object. And at that time, we also observe celestial objects. So this is very exciting thing. And Mark shows me that I have a couple of minutes. I may just tell that research is very important, but when you work at the university, in my case, Auckland University of Technology, education is also very important. So we started astronomy major at School of Computing and Mathematical Sciences. Everywhere in the world, astronomy is sitting in physics department. And what we have nowadays, astronomers who learned about quantum physics and relativity and all this stuff, start writing computer programs, start looking at hardware, middleware, software, networking and all this stuff, because now you can't do radio astronomy without it. So it's our experiment. We just put astronomy major in School of Computing and Mathematical Sciences. We give them a little bit of physics, well, good physics, but not that physics. We give them major astronomical papers because, well, I went through this. I know what exactly they should learn, and we put together a nice curriculum. So, but their main specialty is in computing mathematical sciences, and we have very good people for SKA. They're involved in our SKA research. They do PhDs, a master degree, and research projects in undergraduate level, and so on. So I hope it will be successful. My first year paper, Introductory Astronomy, this year I have 60 students. I started from 12 4 years ago. Right. So yeah, maybe we should go to questions answers. So,
We'll open up for questions and answers now. If we could keep specific to what Sergei spoke about, and if you want to talk deeply about anything in particular, Sergei's around afterwards to answer more questions and talk more about it. I have one to kick off. It seems the agencies are asking us more and more, asking you and yourself more and more to be involved in this tracking.
yeah.
Is that an emerging market or an emerging?
No, actually, I should say that before we started doing tracking, there was another place in New Zealand which did tracking for European Space Agency. It is in Avarua, near Invercargill, between Invercargill and Bluff, it's called, yes, Avarua. And they have, well, ESA just brought and installed the equipment and little antenna, just 4 meters in diameter. Tiny one, you can't use it for radio astronomy really, but for tracking, for very strong signal that comes from the satellites or ESA satellites, that's enough. And the company is called Venture Southland. They do many other things, but one of the things they do is tracking for ESA. So we are not alone, and I think it is a market. It is a market, but mainly we are driven by interest. Like Phobos, is it hollow inside? It's more interesting for us than earn some, a few thousand from something. Yeah. So, but
I want to know now too. Anyone else with questions?
How large is the data set that you capture from the size of radio telescopes that you're using? Like in terms of computer terms, how much is there data to store?
Yes, we don't use too much data. When we have our VLBI sessions, it's normally 24-hour session. Recently we had 1 week session, continuous session, observations. So from one 24-hour session, we have something like 1 terabyte of data. From 1 week, we have a disk pack, and we can do up to 20 terabytes. And the problem is that we should transfer this data to the correlation center. And we do it, and the correlation centers are, the closest is in Curtin, Curtin University in Perth. Another one is in the United States, and the third one is in Bonn, in Germany, and sometimes a few others, but these 3 are major. And we have connection to CAREN network, Kiwi Advanced Research Education Network. It was 2 weeks ago, it was 1 gigabit per second. Today it is 10 gigabit per second. So they just did the upgrade to 10 gigabit per second. That's pretty good speed. Sometimes we do real time. We call it eVLBI. VLBI, very long baseline interferometry. You put little letter E, and it's like real time. You observe, and data from radio telescope, from the receiver, go directly to the correlation center. And this is fantastic. Because what happened before, we recorded, They record it at parks, at some other observatories in the world. And then we send this data. They put this data on the correlator, and they said, oh, something was wrong. And they say it like after a couple of weeks' time. Okay, we start planning experiment again, and we understand, gosh, it was wrong. It was just little tiny thing someone forgot to do. So now we do the so-called fringe check. We start our observations, do fringe check, everything is working. That's like walk with Hobart, fringe, walk with Sparks, fringe, walk with Siduna, fringe, and so on. We have fringes with everyone. It means that we can start observation. It's all working fine. That's beauty of real-time EVLBI and beauty of 10 gigabit connectivity. And actually, in a month or so, RENS is going to upgrade. Is going to upgrade our connection, trans-Tasman connection between New Zealand and Australia, and New Zealand and United States up to 40 gigabits per second. This is about research network. Of course, we have this 1,000 cross cable, which is capable of several terabits per second, but it's commercial. You should pay money. But specifically for research, they allocate 40, will allocate soon 40 gigabits per second. And here we're actually champions. We are better in terms of connectivity than Australia is arranged currently. But of course they're also moving. They have huge amount of money. We suffer about lack of money. Sometimes we come to the government with some proposal and they say, okay, how many radio astronomers are here in New Zealand that would benefit from this? Oh, come on, why? 5, right? But if we talk about tectonic plate motion and earthquakes and so on, and this method that can be used for prediction of earthquake, should we ask about how many radio astronomers would benefit? Stupid. Oh, sorry, please don't record this. All right, more questions, please. Yes.
You usually do observations always together with cooperation with other observatories.
When we talk about astrophysics with 12-meter radio telescope, it is too small to do something, on the frontier. But when we do it in collaboration with others, we are on the frontier and we can publish in the top astrophysical journals. In terms of geodesy, we also work jointly with others. In terms of spaceflight support, we work as a single antenna, 12 meter. But with 30 meter diameter of the dish, you can play golf on the dish. Well, you should walk 30 steps, 1 meter each. Not golf, but I was there a few times. That's quite amazing. And actually, it is smaller than 64 meter parse. I also was there. I actually had a special lift. When you sit on the edge of 64 meter and they start lifting you up there. That's very exciting. So with 30 meter, if you compare 30 meter diameter with 12 meter diameter, okay, what's the ratio? 2.5? 2.5. But here we talk not about diameter, but about collecting area. So 2.5 squared, it is 6.25, 6 times greater sensitivity so almost order of magnitude. And now we are putting cryogenically cooled receiver. It means sensitivity will even increase higher with 30 meter. So people who know all about this area tell us that it is going to be a world class radio telescope. So we are very proud about this development. Okay. 250 meters. to do short baseline interferometry maybe, but at the moment we consider complementary wavelengths. Our or frequencies. Our 12 meter is capable of working in so-called L band. That's where 21 centimeter hydrogen line is based and 18 centimeter hydroxyl maser is sitting. That's one band. Another band is S band, is between 2 and 3 gigahertz, and X band between 8 and 9 gigahertz. But 30 meter will work in C band. It is between 6 and 7 gigahertz, where very interesting spectral lines I mentioned already about methanol based, and this is also frontier of astrophysics today.
Great. Well, thank you very much. Just show our appreciation to Sergei for the first year.
Thank you.
Also, we can all show our appreciation to Winebox and then buy a drink, buy a meal, or whatever you can fit in now. And enjoy yourself. Thank you very much for coming along, and feel free to talk to each other and Sergei as you enjoy your night.
Thanks for
Yeah, good.
Well, I will add to that the Winebox Cafe does some very, very nice desserts. I'll be partaking, but yeah, we'll be around. And if you aren't already on the KiwiSpace newsletter, I've got an iPad over here, so I would encourage you to sign up to be informed of future events. So thank you very much. Thank you very much for coming. We really appreciate it.
Great, thank you.